All right, today we want to talk about titration. Titration is a form of quantitative chemical analysis. Sounds like a big bunch of words. It's really not too bad. Quantitative refers to quantity, so how much of something there is. Chemical is chemical, and analysis is finding out facts about something, analyzing. So if we have a sample of a solution, we don't know, for example, the concentration of hydronium ion in it. We can use titration to solve and determine that concentration. And you can do this. There's many kinds of titrations. There's like titrations where we do acid-base. That's the most common. There are also titrations that we do in Chem 30 called redox titration. But we're obviously not going to worry about redox titration. We're doing acid-base titrations, folks, and acid-base titrations involve an acid or a base that we don't know the concentration of, called the sample, and we're going to titrate it. In other words, we're going to slowly add the opposite to it. We're going to neutralize it. And the reason why that works is our little, very simple acid-base neutralization reaction right here. So we have H3O plus from our acid. We have OH minus from our base. And when we mix an acid and a base together, they neutralize each other and they form a water molecule. So the stuff we add is called the titrant. You might run into other words for it online. I think one of the name for the sample sometimes you get is analyte, but we don't care about that. So in order to do a reaction like this, we need to first understand the neutralization reaction. So remember, different acids create different amounts of H3O. Inside of a strong acid, which are the ones that we really care about in Science 30, whatever the concentration of acid we have is the same as our concentration of H3O. You may remember this from the fact that strong acids ionize completely. In other words, every single molecule of a strong acid will ionize into H pluses and whatever the conjugate base is. So for example, we can use our good buddy HCl. That's a strong acid. On our acid-base table, that's the king right there. That's the highest up. That's the strongest acid. And when we throw that bad boy into some water, it's going to dissociate and it's going to hook up with, ionize. It's going to hook up with the water molecule and it's also going to give us a Cl minus ion. And actually I'm going to tweak this just a touch. Instead of putting that up there, I'll put it here. say H2O bracket L. And I'll make sure that my aqueuses are also all here. So if you remember our Bronsted-Lowry acid-base reactions, HCl in this case is for sure going to be my acid. It's going to be the H plus donor, proton giver. Water is going to be my proton taker. And so my acid, HCl, is going to turn into the conjugate base. And my base, water, is going to turn into my conjugate acid. And the whole point of strong acid is that this happens 100% of the time. So every single molecule of HCl that you put it into a solution or into water, every single molecule will react to make H3O. What that means for us is if we can determine the amount of H3O, we can determine the amount of HCl. And so let's think for a moment. Let's say that our unknown sample is an acid. And if we want to determine the concentration of an acid, we need to add a base to it. Now, if we're adding a base to an acid, remember, acids have a low pH and bases have a high pH. So as we drip base into the acid, think for a sec. What's going to happen to the pH of our little Erlenmeyer flask down here? Well, if we're adding a base, the pH should go up. But here's the next thing we need to worry about. How do we know when the reaction is done? Because what if our base is colorless and our acid is colorless? Like, how can you tell that the pH is changing? Well, that's actually really simple. That goes back to something we talked about last week. We're going to use an indicator. And indicators, if you recall, are chemicals that change color depending on the chemical environment that they're in. And the chemical environment that indicators care about is pH. And remember, pH is just a measurement of how much H3O is in your solution. So as we add a base to our acid, here's our little pH scale, and here's going to be ml of base. So how much base we've added. When we've added 0 milliliters of base, the pH of our solution in here is going to be really low. As we add base, you get this kind of S-shaped curve. And that S-shaped curve is important because at a pH of 7, it means that all of the acid has been reacted with base. And so we call this the equivalence point. So we usually, and for Science 30 for sure, we usually use an indicator that is going to give us some form of color change around thereabouts a pH of 7. One more time, just to recap. If we have an acid in our flask and we're adding a base, our pH is going to go up. In a titration, and I'm going to upload a video of an actual titration being done, so you can kind of reference what I'm saying here with what they're doing and saying on the video. So when you add your acid, or sorry, your base to your acid, we want to stop as close to the equivalence point of pH 7 that we possibly can be. Because if I add too much base, then I've gone too far, I've overshot. Then I have OH in there. I want to make sure that the amount of H3O and OH are exactly the same so that they neutralize and form water. And remember, water, pH of 7, it's neutral. So, in order to understand concentration, in other words, how much chemical is in a liter of water, we do not use grams per liter. We don't use milliliters per liter. We use a measurement that if you were in Science 20, we for sure saw. And that is the unit called moles per liter. The reason why we use moles per liter is because mole is a chemical amount. So 1 mole of one chemical might weigh a completely different, actually it's for sure going to weigh a different amount than a different chemical. So 1 mole of sodium hydroxide is 40 grams. 1 mole of hydrochloric acid is 36.46 grams. They're different molecules, they're made out of different atoms, so they all have their own unique molar masses. The great thing about stoichiometry, and in particular this kind of titration, is that in Science 30 we deal only with strong acids and strong bases, which gives us this sweet little ability here. And we also don't need to worry about grams. All of our stuff is going to be measured in moles. So this is the units that we would use. Moles per liter is concentration. There is a formula that we also use, but the nice thing about it is we can kind of brush it aside because there's a simpler way of doing these calculations. So in the formula we use the variable N, and that's just moles. You may remember that from Science 10 and Science 20. And for the variable V, the unit for V, which is a volume, is liters. So here's the quick and dirty way of calculating a titration. So I'm going to write down a question really quickly here and we'll go through it. So I'm going to stop right here and read it out. A 50 ml sample of acidic pond water was titrated with base that has a concentration of 0.05 moles per liter. Eventually we're going to have to figure out what the concentration of acid in the pond water is. This is important for environmental scientists because it lets them understand what kinds of effects can happen to the life in the pond. If a pond's pH is too far acidic or too far basic, the organisms inside the pond or the lake or the river or the stream or the body of water or the soil will suffer. And so we don't want that to happen. We want these bodies of water to be at their natural pH. So you might see here we have a concentration, we have a volume. It's very tempting to use this formula straight away, but that's not what we are about. We need to know 3 facts to do a titration. We need to know 2 volumes and 1 concentration. So I'm going to finish the asking of this question, and I'm going to give you a volume. The volume of base added was 11.7 milliliters. Now I'm going to give you the easiest way to solve titration, like ever. Here it is. CA VA equals CB VB. This is like the easiest way to do these. So Ca, and I don't mean, that's not calcium, that's a little subscript A. So let me see if I can get it to do a little subby. Boop, there we go. So Ca is, oops, I don't want to be subscript anymore. Ca is concentration of acid. Va is the volume of acid. CB is the concentration of base, and VB is the volume base. So it's a really simple formula. And all we need to do is write down all of our values here and then try to solve for the unknown value. Make sure my pen is right. Okay. So my concentration of acid, I don't know. That's what we're trying to find out. My volume of acid is 50 mils. My concentration of base, and if you're wondering how I know the concentration of the base, it's actually because we have control over the preparation of the base. In other words, we made that in a lab, we measured it, we ensured that it was 0.05 moles per liter. We have control over that. We don't have control over the concentration of acid in the pond water because that's the pond water. So we don't have control over the concentration. But we do have control over the volume. So we measure out 50 mils. Now the last thing we need is the volume of base. So recall, we're adding base from this long tube. This is called a burette, and that long tube is going to drip base into our acid. We're going to have that pH curve, and we're going to use an indicator that will change color when we hit the equivalence point. So the volume of base in our question was 11.7 mils. So if we look at this formula right here, there is a little bit of manipulation that we need to do. We're trying to solve for CA. So the math, the algebra is not hard at all. If I'm trying to get CA by itself, I need to move everything else over. So since these are multiplied, I'm going to divide by VA on both sides. And by doing that, VA is canceled out. Now, I have CA all alone on one side, so I'll rewrite the formula. CA equals CBVB over VA. Done. All we have to do now is plug the numbers in and we'll get our moles per liter. Some of you might be a little bit apprehensive or a little bit worried. You might be saying, okay, wait, Lorenz, these are both in milliliters. How is that going to work? How is that going to play with our moles per liter in the concentration? And guess what? Since these are both in milliliters, they will cancel out. And I'll show you that when we plug everything in. So I have Ca, that's my concentration of acid, what we're trying to find out, equals, okay, Cb is 0.05 moles per liter. That's my Cb. Now I have to multiply by Vb. That's 11.7 milliliters divided by, and then VA, which is 50 milliliters. So everything has been plugged in correctly. Now we have milliliters on the top of a fraction. We have milliliters on the bottom of a fraction. Those cancel each other out. And hey, would you look at that? Moles per liter are the only units that survive the canceling out, the crossing out process, which is, it makes sense. We're looking for a concentration, and it should be in moles per liter. Now all we have to do is the math. So I've got my little calculator in my hand, 0.05 multiplied by 11.7, and then divided by 50. And we get a value that is 0.0117, and since it is a concentration, it's in moles per liter. And then we don't have 3 sig digs in our answer. Ooh, actually we only have 1 because of the way I wrote the question. So that means we only get to spend 1 sig dig. So we can actually say, as the best measurement we have, this is 0.01 moles per liter. Another way of writing that would be in scientific notation, which would be 1 times 10 to the minus 1, 2 moles per liter. So in a titration question, as far as actually doing the math, the actual skill, we are writing down all of the values that we were given in the question. We're writing down our CAVA equals CBVB. We are manipulating the formula to find whichever value we need, whether it's going to be concentration of acid, sometimes it's going to be concentration of base, but we're going to be finding out an unknown concentration. We manipulate the formula, we plug in the values, we complete the math, and we're good.